Thank you to the organizers for this wonderful program and the conference, and for inviting me to give a talk in it. So, this talk is based on work in progress with Henry Lin and Jinping Yang, and it relies heavily on previous work by Berkus, Isachenko, Norovlansky, Torrance, and also by Henry Lin. Okay, so let me start with a brief review of Regge behavior in high-energy scattering at weak coupling. So here the idea is you have some kinematics where you have highly boosted particles that are scattering, but they're not getting deflected very much. So they're pretty much just going along, but they can exchange something which is formally defined as a reggion. And in these kinematics, the amplitude is supposed to go like minus IS to some spin j that depends on the small amount of momentum that is exchanged between the particles. So times some weak coupling coefficient. So this parameter j of t is very interesting thing to try to compute, and this behavior shows up in different areas of physics. It's of interest to people studying QCD, string theory, light ray operators, and conformal field theory, quantum chaos. And it seems like pretty much every time you understand how to compute this thing, you learn some interesting physics. Okay, so we're going to think about this in ADS2. So in ADS2, we're going to have these two particles, and there's no momentum transfer t. There's just an s, and we can label the particle momenta by a p plus and a q minus. And so this expression becomes p plus q minus. And let's go a little bit further and imagine that here are the ADS2 boundaries. And let's imagine that this is a contribution to a correlation function. To compute the full correlation function, we would integrate over momenta with some wave functions, psi in p plus, psi out star of p plus, and some chi in of q minus, chi out star of q minus. We would integrate this expression over p plus and q minus, and we will put a minus 1 here. Okay, so in order to understand the behavior of this correlation function and its relation to quantum chaos, it's helpful to discuss a little bit the symmetries of ADS2. So ADS2 has an SL2R symmetry, and it's convenient to think of the three generators as the following. So we'll have three generators: B for boost, P for like momentum, and E for global energy. This is following conventions in the paper by Lin, Maldacena, and Zhao. So how do these generators act? Well, B acts as a boost, or a Rindler time translation. So this is the picture in Lorentzian ADS2 space. And in Euclidean ADS2 space, it acts just as a rotation. P and E, well, P acts as some spatial translation, and E acts as some time translation like this. So in Euclidean space, P acts like this, and E acts like this, where we put an I in the definition of E. Okay, so these are the three, a choice of three generators for the SL2R symmetry. And I want to emphasize a couple of properties of these from the perspective of the quantum mechanics on the boundary of ADS2, so these two boundaries. So one point is that these are two-sided operators. that are defined as acting on both of the boundaries of ADS2. They annihilate the ADS2 vacuum, which from the perspective of the they annihilate the vacuum, or the equivalent, the thermofield double state. And they commute with the length L, where the length L is defined as follows. So these are two-sided operators, so they act at some point in the Hilbert space, at some point on the boundary, and so we should, really to define them precisely, we should pick 2 points, 1 point on the left side, 1 point on the right side. And for example, P is a translation along the geodesic connecting them. And if we define the operators that way, then they commute with the length between these 2 points. So each of these 3 operators commutes with the length between the 2 points, again viewed as an operator in the ADS2 theory. Okay, the third point I want to mention is that just the SL2 algebra part of it implies that P plus or minus E are eigenvectors with eigenvalue plus or minus 1 under boosts. So P plus E transforms, gets exponentially scaled under boosts. P minus E gets exponentially scaled downwards under boosts. Okay, so let's keep that in mind and come back to this picture discussing the Reggie physics. What I want you to imagine doing is applying a boost operation to the operators that create and annihilate this particle. So we're going to apply the boost operation to those guys, and we're going to boost them by amount t. Yeah, let me. I should have written here that this boost operator is approximately given by beta over 2 pi, where beta is the inverse temperature times h right minus h left. And h right and h left are just the Hamiltonians on the 2 boundaries. So by boosting these, that's equivalent to doing a time translation of these operators on the 2 boundaries. And if we do that, what will happen is the P plus E eigenvalue P plus will just get scaled up by a factor of e to the t. So this expression will become P plus times e to the t times 2 pi over beta times q minus to the j. So the time dependence of this expression will be e to the 2 pi over beta times j minus 1 times t. And this is this exponential growth is the quantum Lyapunov growth associated with quantum chaos. And here we see that the exponent is related to this spin j that appears here. It's important that this spin does not have to be an integer. So in gravity, it is an integer, it's 2, but it in general does not have to be an integer. That's what makes this Reggie limit so interesting. Okay, so that's some introduction to this Reggie limit and the symmetries of ADS2. What we're going to be doing in this talk is trying to discuss a couple of puzzles associated to this and to another thing I'll explain in a second in the context of the SYK model, the large P or large Q SYK model. And I can mention one of the puzzles here, which is that in the large P SYK model, we get a similar, formula very similar to this, except that instead of this factor here, we get something that looks like P plus Q minus times minus I e to the 2 pi over beta t to the j minus 1. So instead of raising this whole expression to the power j minus 1, we only raise this part to the power j minus 1. We do not transform the momenta in that expression. And that looks very funny. It looks very funny because from this perspective, the transformation of momentum under time translations is fixed by the symmetries. So it looks like this expression in large P SYK is somehow violating our expectations for how the symmetries act. And trying to understand that will be one of the puzzles that we're trying to resolve. The other puzzle, I don't really have room to write it, so I'll just say it, is the following weird feature of large P SYK model. If you think about the thermal circle where the correlators are defined as some circle, try to imagine that it's drawn there, and let's think about the two-point function as describing 2 points on the circle, and we can move them around. Then normally, as you take the 2 points and bring them together, you expect some kind of a singularity. But in the large Q SYK model, what happens is the correlator is actually completely smooth at that point. It can be analytically continued further. So it can be analytically continued further, and there's a singularity at some finite distance where the operators have crossed each other. So there's this extended domain of analyticity. And so these are two sort of funny features of the large PSYK model, this funny thing and this. And we're going to see that those two things are related to each other and are related to this fake geometry that will derive from some algebra in a moment.
Excuse me. Can you look at the region where it's not necessarily maximally chaotic or the gravity description?
Yes, that's right. Right, so there's a regime in the SYK model I'll describe in a second where this J is 2, and then there's no puzzle here, but it can also not be 2, and then there's a puzzle.
The domain of analyticity is bigger than the strip of weight beta.
Yes.
How big is it?
It depends on the temperature. So that will be explained. There's one other thing which I want to mention at this point. No, maybe I shouldn't mention it. Yeah, I think I won't mention it. Let's just move on to discussing the SYK model. And please do continue to ask questions. I think I've kind of lost whatever ability I had to give talks, so questions are very much appreciated. So the double-scaled SYK model is defined as an ensemble of Hamiltonians of the following form. We take some random tensor with p indices, antisymmetric tensor with p indices, random coefficients, and multiply them by product of p fermions, and sum over all the choices of indices. So there's two parameters. There's the number of fermions in the interaction, p, and there's the total number of fermions that you can pick from, which is n. And the double-scaled limit is a kind of a funny limit where you take both of these parameters to infinity. But you hold fixed this function q. Q is the exponential of minus 2 times p squared over n. Basically, you hold fixed p squared over n. You take both p and n to infinity. And a very useful parameter to discuss in that limit is this parameter q. Okay. Now, when q is close to 1, so think about q being close to 1, that is like n is very big. In that limit, this is basically that's a classical limit of this model, like more like a conventional large n limit. And in that limit, we can discuss some simple properties of the model. So here I've sketched for you the energy. So the x-axis is the range of energies, and the y-axis is the density of states. Just sort of a cartoon of what it looks like. And the energies range from minus n over p squared up to plus n over p squared. And you can write it as minus n over p squared times sine of pi v over 2, where we've invented some parameter v. So v equals 1 is down here, and v equals 0 is in the middle here. Okay, so low energies corresponds to v equals 1, and 0 energies, which is like very high temperature, infinite temperature, corresponds to v equals 0. And you can compute the Lyapunov exponent. So here, Lyapunov exponent is 2 pi over beta times j minus 1. You can compute the Lyapunov exponent, and you find that it's given by 2 pi over beta times a parameter times this v. So that can be rewritten. Don't worry if you're not following memorizing this exactly, but that can be rewritten as 2 times cosine of pi v over 2. But the important point is more this formula, that it can be less than 2 pi over beta. So over here on the left side, when v is 1, the Lyapunov exponent is 2 pi over beta. That means j is equal to 2. That's like gravity. But elsewhere in the spectrum, the Lyapunov exponent is less than 2 pi over beta. So it's this case where j is less than 2. So down here, we have jt gravity. And like in the rest of the spectrum, we have some kind of question mark. And we would like to try to explore this question mark. That's part of what we're trying to do. OK. Any questions about this SYK setup? Yeah.
How do you choose V?
How do you choose V?
Yeah, let's say you want to ask some physical question. What do you ask to pick V?
Yeah, so that means that what you need to do to pick V is you need to sort of focus in a particular range of energies in the spectrum. So you can do that by adjusting the temperature. So the relation between V and temperature is actually given by solving this equation for V in terms of beta, or beta in terms of V. So you can either fix the temperature or you can fix the energy. But either way, you focus attention on part of the spectrum here, and the corresponding energy gives you V. OK. So what I've said so far is actually similar to the, not so important that we've taken this double-scaled limit. P is very large. But there is something nice that happens in this limit, which is that the model becomes solvable, and it becomes solvable by a very direct attack. So I'll try to give an indication of how you solve it. So let's first imagine computing trace of h squared. So we take 2 copies of this thing, compute trace of h squared. So the 2 copies of h are represented by dots, and the circle here represents the trace in the Hilbert space of the fermions. So the way you organize it is you imagine doing Wick contractions of these random J tensors. There's so many indices here, and n is so large that you can averaging over this system is extremely self-averaging. So we can imagine integrating over J and connecting these things with lines for the Wick contractions of the J indices. So that Wick contraction sets the indices of the fermions here equal to the indices of the fermions there. And then the trace just gives some constant, which I'm going to call 1, to distinguish it from something we'll see in a second. OK, so now let's imagine computing trace of h to the 4th. To compute that, we put 4 of these dots for the Hamiltonian. And now we can contract in a few different ways. We can have this Wick contraction, we can have that Wick contraction, and we can have this Wick contraction. So these ones give 1 because these fermions get set equal to those fermions, and then you can move them next to each other. They multiply to give the identity. These ones the same. So this gives 1. So this is equal to 1 plus 1 plus this diagram is new. What happens here is you have to figure out how likely the fermions here and the fermions there are to share some indices. By summing over the number of indices that they share with a factor of -1 to the number of indices in common, you get a factor of q. OK. So this diagram gives 1 plus 1 plus q. Let's see now how to compute something with some operator insertion. The trace h squared times some operator, h squared times operator. Here the operator is going to be a product of p times delta fermions. So p is the number of fermions in the Hamiltonian, and delta is a parameter. So we have the following kind of situation. So we have 4 dots for the Hamiltonian, and 2 extra dots for the O operator. And the diagrams you draw, you connect the O operators together. And then we can have the same types of H contractions. So this one gives us a factor of 1. This one gives us a factor that involves the crossing of the matter line with the fermions. That gives Q to the delta. Each crossing gives q to the delta. Here we have 2 crossings, so we get q to the 2 delta. And then this line here gives us q to the 2 delta, but also the Hamiltonian lines cross once, so we get q to the 2 delta plus 1. Okay, so this gives the exact answer in the double-scaled limit. And you can imagine computing correlation functions by taking, product of e to the minus tau h times an operator, e to the minus tau prime h, expanding that thing down in polynomials in h, and then using these types of rules to evaluate them. And actually, it can be done. Explicitly. That was achieved in this paper. Actually, writing explicit formulas for that involving some special functions. Okay. Part of the method that they use to solve it is to associate a Hilbert space to the chord diagrams. So that's the kind of the key idea in solving this, in doing this for arbitrarily large numbers of Hamiltonians and operator insertions. So let me explain how that works. So here we have some relatively complicated chord diagram where this yellow thing is an operator, an O line, and the rest are Hamiltonian lines. And to associate a Hilbert space to it, what you imagine doing is picking 2 lines in the circle and picking 2 points on the circle, and then connecting them by a line that cuts through the chord diagram. And the rule for the cut is supposed to be that this is a rule that kind of, it's like a gauge choice for the type of cut that you can make through the chord diagram. The rule is that any chords that cross your cut cannot have previously intersected each other. So an illegal line would be to draw this line above this crossing. But I'm allowed to draw it below the crossing. And similarly for the top cut, no chords that cross this blue line here can intersect each other in the future. So that defines where you can put this initial and final slice. And we can think about a Hilbert space living on this. Let's think about the lower slice for a second. Hilbert space living there, just labeled by the number of chords that are intersecting that slice. So in the case with one matter particle, the Hilbert space can be characterized by a pair of integers, n left and n right, where these are the number of chords to the left of the matter chord and the number of h chords to the right of the matter chord. So we have these vectors, n left and n right, and you can picture them like this, where we have n left chord, h chords to the left, then we have a matter chord, and then we have n right chords to the right. So in this example here, we would have n left equals 1 and n right equals 2. Okay. And we'll define n as the sum, n left plus n right. And n is like it's like a length between the two sides. It's like this chord geometry defines a kind of discrete geometry. And you can think of n as the length between the two sides. One way to motivate the thinking about that as the length is that the penalty factor for some matter line crossing from the left to the right would be the number of chords it intersects. And so the number of chords it intersects, it would give some factor. We would get some factor q to the delta times n for some matter line crossing from the left to the right. And that would give a contribution to the 2-point function that's like q to the delta times n. And we should compare that to like e to the minus delta times the length for a 2-point function. So we see that n is linearly proportional to the length between the two sides. Okay, so there's some kind of discrete geometry which you can associate to these chord diagrams, and it's an kind of an analog of the geometry that you get connecting these 2 points in ADS2, the 2 sides on the boundary in ADS2. So what we would like to do is we would like to build analogs of these operators, and we would like to use those operators to solve our puzzles. So we'd like to understand this algebra, and then from the algebra understand the geometry and the resolutions of these puzzles. Let's discuss how to define this algebra. So algebra is constructed out of the n operator, and the left and right Hamiltonians. So the left and right Hamiltonians act simply on this Hilbert space. For example, if we act with h left on this state, then what it can do is it can add a new chord. So we can have a dagger L, or it can annihilate one of the left chords. That gives a factor AL times 1 plus Q squared plus Q to the NL minus 1. Or it can annihilate one of these chords, plus A right times Q to the delta times Q to the NL plus Q to the NL plus 1, and so on. So this gives some explicit expression for the left and right Hamiltonians in terms of raising and lowering operators on the left and right sides. You use that formula for those Hamiltonians and construct the following generators. B is equal to, let me just put a constant here, times HL, commutator HL, commutator N, minus left interchange with right. E and P are similar expressions. Let me not write them in to save a little bit of time. So these are three operators you can write down that have the following properties. These are two-sided operators, just the same as these B, P, and E are, because they depend on the length operator, which is a two-sided operator, and also the left and right Hamiltonians. They annihilate the thermal field double, and you can check that they commute with n, which is a discrete version of the length between the two boundaries. So those properties are the same, but they form a complicated nonlinear algebra. So we're not mathematicians. I think we're a little bit out of our depth. I need to make an appointment to talk to a mathematician. But it's kind of a complicated linear algebra. At the level of algebra, it's a subalgebra of the UQ SL2R quantum group. But it is not actually itself a quantum group. It has finite dimensional unitary representations which correspond to these things. States with constant n left plus n right. Okay. The important point for our purposes is that in the limit, yeah, I'm not sure how to explain the rest in 3 minutes. Let me think for a second. Okay, let's do the following. There's a limit which we can take where we take q goes to 1, n goes to infinity, with q to the n over 2 equals cos pi v over 2 held fixed. So that's a limit where this continuous geometry, discrete geometry becomes continuous because n is being taken to infinity, q is being taken to 1. And in that limit, this weird nonlinear algebra actually becomes SL2R. Becomes SL2R algebra. And we can ask how that SL2R algebra acts on the boundary. And this is the main point I want to explain. It acts in the boundary in the following funny way. Let's take the actual physical boundary of length beta, going from 0 to beta. This is where the operators live in the thermal circle. And we can think about an operator living here in the bra, and an operator living here in the ket, and an operator living here in the bra, some matter operator. Take this space and cut it in 2 pieces. Put the bra up here with the matter operator. Put the ket down here, and then add some filler to make a complete circle, where the length of the full circle is equal to 1 over v times the length of the portions that we cut from here. So it's a larger circle that you form by pasting together these halves with two fillers. And the claim is that the SL2R algebra associated to these operators in this limit is just realized as the ordinary SL2R algebra that we defined before on this big fake disk. So there's a big fake disk where these symmetry operators just act as ordinary SL2R transformations. And that explains both of the puzzles. Let me just sketch why it explains the puzzles. Let's start with the Lyapunov exponent puzzle. The operator beta times h left minus h right is an operator that takes us all the way around this boundary. So that's an operator that takes us from here to here, and then again from here to here. But that's not a full 2 pi rotation of this disk. That's a 2 pi rotation times v. And so that means that the time evolution operator here does not really act as a boost of the disk with the standard normalization. It differs by a factor of v. And that factor of v explains this different Lyapunov exponent. So that is one of the puzzles. The other puzzle we were trying to understand is this two-point function, this extended domain of analyticity of the two-point function. And this gets into the part of the reason why I think this picture is interesting, which is that look at the locations of these operators here, and let's draw them on the fake disk. So we have this one here and this one here. We can move these towards each other. And we move them towards each other all the way to this point here. That corresponds to putting the operators here and here. And it looks, from the perspective of the thermal circle, like that's all you've got. But you can see on the fake disk, on this fake extended boundary, you can keep moving them. And there's a singularity only when they approach each other on this extended disk. So placing the system on this this expanded disk here encodes the extended domain of analyticity of the two-point function, and also explains this submaximal Lyapunov exponent. I did not have time to explain some other things, but I want to end on time, so thank you.
Thank you, Douglas. Questions? Yes.
So this boost operator doesn't seem to be just h left minus h right, right? Then how would I understand that generate a time evolution that bring one pair of operator to the other pair of operator?
Yeah, the boost operator is approximately given by a multiple of h left minus h right. So it's basically a multiple of h left minus h right times this factor of 2 pi v over beta.
Oh, you mean that boost operator right
This operator here. Yes, it's not obvious from this description, but near the thermofield double state it is. So,
I see. Yeah, thanks.
Actually, maybe I have a remedial question. So with higher dimensional gravity, in a sense, it doesn't really regiize because it iconalizes before it regiizes, or similar physics takes place. So remind me, is there any analog of that in this case, or in the JT case, or?
I'm not sure. Sorry, it iconalizes before it regiizes.
Yeah, it's because if you
well,
want a big momentum transfer, you get it from an exchange of, say, a large number of very soft quanta if you're looking at the high energy limit. Very soft gravitons, basically, that build up, something like the Eichelberg-Sechsel.
I guess you don't want a large momentum transfer. You want a small momentum transfer.
Well, if we're thinking about high energy scattering, you want to, I think, go into the regime of higher and higher energy, higher and higher momentum transfer.
No, the momentum transfer stays fixed, and the longitudinal momentum becomes large. So it's like fixed T and large S.
Yeah, I guess the question is how big you're fixing T at, maybe.
Something. Well, for here there's no T, but in general, some order one to discuss the regular limit in general.
So something like Planckian, yeah, okay.
No, not Planckian, like something smaller.
Okay. Yeah, other questions?
So if you consider a 4-point function instead of a 2-point function or some other higher point function of the matter field,
Yeah.
What would the fake disk look like? Would it have 4 missing pieces instead of 2?
Yeah, that's a good question, and we don't know. Basically, we don't know at this moment how to compute the 4-point function using the fake disk, or what that looks like. We know how to compute the 2-point function, how to realize the symmetries acting on one single particle states. That's enough to get the Lyapunov exponent, but it's not enough to get the full 4-point function. So yeah, we understand some aspects of, Henry understands some aspects of multi-particle states, and that goes part of the way to answering your question, but let me not try to explain that now.
I just want to ask some questions to understand the logic. So you wrote down these symmetry generators, and in this classical limit, they give an SL2, and the fake disk is just encoding the action of that SL2?
Yeah.
Okay, so it's a diagram that you write down to explain the SL2 algebra.
Yes.
Why these generators, and could there be some other generators that encode a different SL2 algebra with a different fake disk? Or what's special about those formulas?
Special about these things, they commute with n. And they satisfy some closed, although nonlinear algebra. So in that sense, they're analogous. They're analogous to the SL2R generators in ADS2 that I defined at the beginning. So the special thing about those things, they commuted with n, they form some closed algebra, and they act on this two-sided Hilbert space. And one of them is approximately the Hamiltonian, h left minus h right. The same is exactly true of these things, just the algebra is more complicated.
And so is there a lesson for some, so suppose we have some other theory and we want to find like the ADS isometries inside this other theory, might we encounter this phenomenon?
Yeah, maybe so. I think the interesting thing here is that there is a geometric, well, one interesting thing is there's a geometrical realization of the Ruggion, or like the kind of like the thermal analog of the light ray operator, which is, it's the P plus of this fake disk. And normally you do not have a simple picture like that. So it's again, it's a simple picture for that thing. And I would guess that in the SYK model in general, not at large Q, it's probably a little bit of both kinds of things are happening, where there's a little bit of fake disk and also some more conventional kind of stringy-like correction of the Lyapunov exponent. In large Q, the stringy-like part is gone, and you just have this other thing. Kind of interesting thing for us is that there is this other thing, which we didn't know to try to find.
Yeah, this is just also a question to clarify the kinematics between the fake and real kinematics. So if we work at the canonical ensemble with inverse tensor beta, we expect that Minkowski correlator with different operator ordering are related by KMS condition. Mm-hmm. That relation is satisfied with beta, not the fake temperature, right? Mm-hmm. Mm-hmm. The real beta?
Yeah.
Okay.
So depends whether you change the operator ordering.
Yes.
So you can, if you start from here and go around to here, then that's like the usual KMS condition here. But there's another one you can do where you have operators on the fake disk and you go around, and at some point you kind of cross.
Yes.
But you don't worry about the fact that you cross. You just keep going. You keep going with analytic continuation, and you reach this point, and then there's another KMS type condition at that point.
And somehow that second KMS-like condition is the one which is more relevant to understand large time. Or this,
yeah, that's the one that is relevant for the Lyapunov exponent. Right. That's the one that determines the Lyapunov exponent.
Okay, thank you. But you still have, in some sense, both of these KMS-like conditions are valid.
Yes. Yes.
Thank you.
Yeah, this is probably a very stupid question, but I had thought that the SL2R that we see in the SYK theory at all is something that, to the extent that it exists, emerges at very low energies.
Yeah.
Now you're away from this very low energies.
Yes.
So why doesn't this just get broken? Why do you find something deformed?
Right. Exactly. So why isn't it broken? Why do we have this SL2R that persists even at finite temperature? So in the standard SYK model, you don't. But in the large P SYK model, you do. And somehow that model continues to have this SL2R symmetry of the fake disk. So it's like a different SL2R, but continues at all temperatures. So.
Did you know before you did the calculation that you would get? Did you expect this from general principles, or something that just comes out of calculation?
Yeah. Well, I don't know about general principles, but there have been hints of this in previous computations. For example, the 2-point function of the large Q SYK model at finite temperature is just, it looks kind of like the conformal 2-point function, but with some funny rescalings. And a precise statement is that it is the 2-point function on the extended disk. So that is, there's some SL2R invariant 2-point function, 1 over sine squared of 1/2 theta on this disk. And that is the 2-point function of large Q SYK. So that's an indication that there's some version of the SL2R symmetry even at all temperatures, but it wasn't understood very precisely.
So in the Q goes to 0 limit, the very different, the opposite sort of extreme, where you don't have any intersections at all.
Yeah.
Those are like the planar diagrams of a matrix model.
Right.
Is there a geometry in that limit, perhaps? Is that something you think that could be an SL2R there in some sense?
No. So there, what you get is so I said that here this is like a subalgebra of this UQ SL2R. So there, if you hold Q fixed, or you take it small even for large N, that becomes that actually becomes the exact quantum group. So the symmetry that you have there is the UQ SL2R, the full thing. And
there's no simplification as Q goes to 0?
Well, it depends a little bit what you're holding fixed. Whether holding fixed the number of these chords. Yeah, as you say, it becomes a the model in that case. Yeah. So what happens in that limit? So what happens in that limit is basically this matrix here becomes a conventional random matrix. Like, it's not, so for finite P, this is not, it's some kind of sparse random matrix ensemble, because it's built out of products of relatively few operators. But if we imagine the Q goes to 0 limit like you were describing, then Q goes to 0 is like taking this P parameter extremely large. So the Hamiltonian is kind of no longer sparse. It's like just an ordinary Hermitian random matrix. That's kind of the other extreme. I don't think there's well, I guess you've explored a type of worldsheet geometry or worldsheet theory related to that kind of matrix integral, but.
So that's why I was curious to see, because in some sense there's an SL2R mod U1 coset worldsheet theory that is perhaps the dual. So I was wondering whether that is perhaps in some way related to some emergent geometry here. But yeah.
Okay. Yeah.
Okay. Is there maybe a final question? And you want to start set up?
In the beginning, you mentioned that in the OTOC you change the power of e to the t, but not the power of PQ.
Yeah.
And I see how this changes the power of e to the t, but maybe I missed it. But you say
Yeah,
why you get
everything
this funny
everything
behavior
else
with
stays the
PQ.
same. So everything else is just, these are the wave functions, psi p, these are the wave functions for these operators on the fake disk. And as you change the temperature, what happens to this fake disk? It stays the same. What happens is this region shrinks. So it's like this whole thing stays exactly the same, just the part of it that you call the physical boundary shrinks above and below, and that affects the relationship between the time translation operator and the boosts. But the wave functions and everything else are just the same.
I see. Thanks.
Okay, well, let's thank Douglas again.